Okay. Yeah, well, I thank the organizers for this really exciting conference and also for inviting me to kick off the session here on beyond the standard model physics searches with different quantum sensing techniques. So I'll talk about a few things we're working on in our lab. But first, just to set the stage, if we look at the standard model, it does a very nice job accounting for the building blocks of matter and the known forces of nature. And if you talk to my experimental colleague, Geraci, he can tell you through precision measurements of the electromagnetic moment that we can actually do comparisons between experiment and theory that are at the part per trillion level. So it's really quite remarkable that we have this level of understanding of a theory with comparison in theory and experiment. But of course, there are many unsolved mysteries. In particular, we have no idea what makes about 95% of the matter energy content of the universe. We don't know what dark matter is made of, except that it's there and apparently 5 times more prevalent than the ordinary matter. Using the same theory that we have this high precision comparison at the part per trillion level, if we use it to estimate the dark energy, we're wrong by about 120 orders of magnitude, which is a little bit embarrassing. And as we already pointed out earlier, we don't know so well how gravity really interfaces with the other standard model forces or quantum mechanics. And so gravity is one of the things we're interested in looking at in our lab. In particular, if you look at the relative strength of the 4 known forces of nature, say for 2 protons inside of a nucleus, there's a huge disparity in the ranges of interaction strengths. In particular, gravity is about 36 orders of magnitude weaker than electromagnetism. And so this is known in the theory community as the hierarchy problem. Why is gravity so small compared to these other forces? And it really requires an extreme amount of fine-tuning in the standard model to get a reasonable value for, say, the Higgs mass. And so there have been some theories of physics beyond the standard model which can alleviate this fine-tuning problem. And one way of testing those theories involves doing measurements of gravity at short length scales, in particular to find some hints of new physics that might solve this hierarchy problem. And so if I just write down the Newtonian potential for 2 masses, where I have the Newton constant and then 1 over the separation distance, there are several theories beyond the standard model which suggest that we'll see some correction term, which is what I have in parentheses here. We have some new physics with some dimensionless number alpha, which is just telling you how strong the interaction is compared to ordinary gravity. And then you have some range of the interaction, that's basically the Compton wavelength of the new particle responsible for this interaction. And so several theories beyond the standard model point to the sub-millimeter regime as sort of a natural place to look to suspect such deviations, in particular things like supersymmetry, which can, or string theory, or also theories of perhaps large extra spatial dimensions with particles that would be living inside of them. And one can also think about this in some way as some sort of new 5th force, or if you like, a violation of the Einstein equivalence principle. So experimentally, this is not so simple for a couple of reasons. The first of which just has to do with how weak gravity is, which is sort of what led us to the problem in the beginning. And so if you look at how the gravitational force scales between 2 spherical masses, if you shrink the whole size of the system down, plugging in the fact that the mass has some finite density and size, the Newtonian force between these 2 spherical particles is scaling like the positive 4th power of the size scale. So if you make the system really small, the force gets weak very, very quickly. And in particular, at the sub-millimeter regime, say, for example, at the 10 micron kind of length scale, the force you're trying to measure here is about 10 to the minus 21 newtons, or a zeptonewton. And so this is billions of times smaller, for example, than atomic force microscopes typically measure, and it's extremely challenging to measure such tiny effects. At the same time, while gravity is getting so weak, other background electromagnetic forces are actually getting stronger as you bring things closer together. In particular, we're concerned about effects such as the Casimir effect, which is interesting in and of itself. So you have a macroscopic manifestation of quantum vacuum fluctuations. So for example, if you take 2 parallel conducting surfaces, even with no electrical potential between them, in the presence of the quantum vacuum, you have modes that are being created and annihilated. Certain modes are allowed inside the space between the plates, other modes are allowed outside, and there's a net pressure basically which causes an attractive force between the plates that drops off like 1 over the 4th power of the separation. So at the length scales that we're interested in, this force can be orders of magnitude stronger than the gravitational force that we're looking for. In addition to this interesting effect, there are some perhaps not so interesting, more dirt-like effects that one needs to worry about in these types of experiments. In particular, you can have local work function variations over the surface of conductors, so-called patch potentials, which can lead to other spurious electromagnetic background signals, which poses a challenge. And so if I look at the kind of state-of-the-art for testing these types of corrections to the Newtonian gravity at the sub-millimeter kind of length scales, here I have the range of the interaction going from 100 microns down to about 10 nanometers. And on the vertical scale, I have this parameter, strength parameter here, how strong the new interaction is relative to gravity. So I have gravity here all the way at the bottom. So this is for a new interaction that's equal to gravitational strength. The area here that's shaded in the yellow is what's been ruled out in previous experiments. And so at the largest length scales here at tens of microns, there's nice experiments done at the University of Washington using precision torsion balances. At slightly smaller length scales, there have been cryogenic microcantilever experiments like the one here that I took part in as part of my PhD research. And then at even shorter distances, there are limits that are set from Casimir measurements or adaptations of Casimir type experiments. And some of the theories that are predicting new effects here have their predicted parameter space here shown off on the left. And so all of these sensors here are relying on some kind of mechanical element, whether it's a cantilever beam or a torsion fiber or a torsion oscillator. And these mechanical sensors are limited in terms of their intrinsic sensitivity just due to thermal noise. And so just like you have, for example, Brownian motion of a piece of dust that's being kicked around in a fluid as it's meandering through a fluid, in the presence of a finite thermal bath, finite temperature bath, this oscillator is given random kicks by the environment just due to the thermal energy. And if you write down the acquisition theorem from statistical mechanics, you can derive that in the presence of these random thermal kicks, there's a certain minimum force that one's able to resolve in the presence of that background. That force goes like the thermal energy KT times the spring constant of your mechanical system times the measurement bandwidth divided by the frequency and the mechanical quality factor of the system, which is a measure of how much dissipation there is. So one way to improve your sensitivity is to get rid of the mechanical dissipation. And so in these types of systems that have been used in gravitational tests, typically involving some sort of clamp mechanical oscillator like a cantilever beam, there are a few different mechanisms that cause loss in the system. So in particular, there's clamping loss, surface imperfection, and also internal thermoelastic dissipation in the material. And so as a way of getting around this limitation, one can think about using techniques from the AMO community, in particular, using optical trapping to replace this clamped solid state system with actually an optically levitated system. And so here you have a dielectric particle that you can actually suspend using the radiation pressure and now study how its motion is sensitive to external forces, where you're now no longer limited by these dissipation mechanisms from connecting to the environment and internal materials properties. And so of course this field goes way back to the 70s with pioneering work from Art Ashton and collaborators at Bell Labs, and that work spun off into the field of optical tweezers, which of course has had a big impact in areas like biology and biophysics. He did a little bit of work working on particles in high vacuum, although most of the early work concerned particles in a fluid. And of course this early work also led into the modern field of laser cooling and trapping of atoms in some way. But so in a high vacuum, basically what you can do is take a neutral glass particle and you create a potential where essentially you have a strong field seeker, so the induced dipole moment of the particle wants to trap the particle essentially at the focus of a laser beam. And so when you do this, you essentially can, for a spherical particle, realize essentially three independent harmonic oscillators that are confined in some laser trap. And then the sizes of object that you can trap range from tens of nanometers all the way up to tens of microns. And in particular, if you can get in a high vacuum limit, you can get very low friction from gas collisions, in principle getting quality factors as high as something on the order of 10 to the 12th. And you can also study and devise ways to cool the center of mass motion temperature of these objects in these types of traps. And so if you look at the ground, if you want state of the art, there have now been a couple groups that have recently demonstrated cooling the motion of the particle all the way to the quantum ground state of its potential in a couple of different approaches. So in addition to being able to access this quantum regime for the motion of these relatively macroscopic objects, you can also study how they behave as force detectors. And so here now I've rewritten the same equation I had earlier in the talk for this thermal noise limited force sensitivity, except now written in terms of the gas background gas damping coefficient gamma and then the mass of the particle. And so I'm plotting here this minimum resolvable force as a function of the size of the particle going from tens of microns here down to 10 nanometers. And then this is the force here on the left side, the corresponding acceleration sensitivity on the right side. So if you have a micron-sized particle, you can measure forces that are on the order of 10 to the minus 21 newtons per hertz, which is really in the interesting range for testing these gravitational type of signals. And so these other solid-state systems that have been used for these type of measurements have sensitivities that are a few orders of magnitude higher than that. So if you look on the right end of the graph here, the line I'm plotting for the minimum force actually deviates from this thermal noise limited slope here due to another effect, and this is basically due to a heating mechanism from photon recoil. So the laser that's trapping the particle still has finite number of photons, and due to basically shot noise, there's a photon recoil and essentially a momentum diffusion of the trap laser photons, which also can deteriorate the sensitivity. But nevertheless, even considering that, you can see here for quite a range of sizes, you can get down into this interesting regime for the gravitational measurements. So experimentally, we collect the particles essentially by shaking them from a substrate using a high power pulse power generator, which is shaking a piezoelectric ring. So we have particles deposited on the surface, and it turns out we have to shake the particles quite vigorously to knock them off the surface. And so in particular, for the particles that we're using in these experiments, we have a diameter of about 300 nanometers. It turns out that the acceleration you need to break the van der Waals stiction force goes like 1 over the square of the radius of the particle. And so we're actually applying about 10 to the 7 Gs of the surface acceleration to this thing to knock the particle off. And so when you do that, here's a movie of one of the systems where you can basically see the particles kind of raining down over the trapping area. Hopefully this movie will work. It's not looking too promising here yet so far, unfortunately. Here we go. So yeah, so you can see particles are falling down from the substrate until you see one of them landing into the area where the optical trapping beam comes to a focus. And so what you're looking at here, this is a movie done in real time. It's not slowed down or anything like that. And so there's a little bit of gas, nitrogen in our system to basically damp the motion of the particle so that it can find its way into the trapping minimum and not just simply ballistically fly through it. Then in order to get this high sensitivity, we actually have to remove the gas from the system. And so in order to do that, we have to stabilize the particle while we do that, and we do that using laser feedback cooling. So basically we detect the position of the particle by focusing the scattered light from the particle onto segmented photodetectors. This allows us to measure the instantaneous position of the particle, which we can then figure out the instantaneous velocity of the particle, and then using acoustic modulators, we apply a velocity-dependent damping force, essentially, to introduce damping into the system while we evacuate the gas. And so this allows us to stabilize the particle and get into the high vacuum limit. And so when you do this, it turns out you may worry that you are spoiling your force sensitivity because you're introducing laser damping. However, what you're essentially doing is reducing the temperature of the particle while at the same time the quality factor, and so the ratio actually winds up staying preserved with this cooling, and so you get to keep the same force sensitivity that you had originally. So once you apply the feedback cooling, then so here's some results showing that in the high vacuum limit, where we showed that you can basically measure forces down at the zeptonewton or 10⁻21 Newton level. And so this work here is using a standing wave trap where we have counterpropagating beams forming an optical lattice trap essentially. And so most of the particles that we trap have no electric charge, but occasionally we have 1 or 2 extra electrons that are on the nanoparticle. And so if we apply a known electric field, we can essentially calibrate the force sensitivity here for the case of 1 or 2 extra electrons. But so if we have no charge, we can integrate down to the forces that are on this order of zeptonewtons, which is quite promising for this gravitational test. So we're using this now as a test mass in a gravity experiment that's currently running. And so what we have is a 300 nanometer piece of silica, and we create a retroreflected optical standing wave by bouncing a laser beam off a surface, and we trap the particle in one of the antinodes of the standing wave, in particular at the closest antinode, which is about a quarter laser wavelength away from the surface. And so in that case, the surface for us is a gold-coated silicon nitride membrane, which is less than a micron thick. And then behind the surface, we have a device that we use to source a gravitational signal. In particular, it's a drive mass composed of different sections of alternating material, gold and silicon, which have a pretty big density contrast. And so as we oscillate the device back and forth, we basically create a time-varying gravitational force on the test mass due to the different densities of the pattern that are passing behind the screen. And so with this system, we're aiming to get a few orders of magnitude improved sensitivity for these Yukawa type corrections to gravity at the micron kind of length scale. And there's some other work using slightly different arrangements that's ongoing at Stanford and Yale, for example, where they're using slightly different geometries and larger particles aiming at slightly different, longer length scales, but with a similar essential idea. And so here's a picture of the inside of the experiment. So we have counterpropagating lasers forming a focus, and then we trap one of these nanoparticles in the focus. And then so to load it next to the surface, what we do is we have here's the silicon nitride membrane. It's on a chip here that has a knife edge. And so we essentially insert this on a movable stage into the beam, where we cut through the laser beam using the knife edge basically right next to where the particle is sitting. And so depending on where you slice the mirror into the trap, you can essentially control which antinode the particle gets loaded into. And then behind the screen, then we have another stage which we can approach the drive mass device. Here's a picture showing one of the drive mass devices in the middle of the fabrication process, where here we have the different density materials. So these are electroplated gold trenches inside of a silicon wafer that we then we then polish flat and then put gold on the top to create a nice uniform electromagnetic surface. So this device moves back and forth behind the mirror, and then on the front of the mirror, we also have the ability to essentially scan over the position. So we can basically do a scanning force microscopy using the nanoparticle as a sensor above the surface. And so basically what we can do is study the force noise spectrum as a function of distance from the surface. So these are loading in particular antinodes of that standing wave potential at distances ranging from a sub-micron up to tens of microns. And we can also, with a stage, we can actually also study moving the particle around in the plane parallel to the surface. And we think this is going to be a very useful tool to map out the local electromagnetic environment, in particular from patch potentials, which should help us understand the systematics in the system. So at least for this results here, we've seen no significant excess force noise within our measurement frequency range of interest, at least at the attonewton level, and we're continuing to do higher sensitivity measurements, and the experiment's actually running on that actually right now. So we're hoping to have something more soon on some initial limits from gravity there, but I wanted to switch gears and mention one of the other, I think, exciting applications of this kind of force sensing with nanoparticles in particular. One can also imagine using these sensors to look for gravitational waves, but in a frequency regime that's higher than the range that the LIGO type detectors typically are searching for. And so basically the idea is that you can trap a nanoparticle inside of an optical cavity, where now you have some antinodes of the trapping field representing locations where you can trap a particle. And so if a gravitational wave comes along, it basically changes the physical distance between the mirrors. And this creates a force on the nanoparticle because it moves the location of where the optical trapping field antinode is with respect to the particle. And so the particle basically gets kicked around because the moving end mirror of the cavity is causing the trap minimum position to deviate from where the particle is sitting. And so there's an enhancement that we get when the optical spring restoring force frequency here actually coincides with the frequency of the gravitational wave that's passing. And so in this way, you can think about it kind of like a optical trap version of the older style of gravitational wave detectors, which are these Weber bar type detectors, where basically they ring like a bell if a gravitational wave with the right frequency comes along and excites it. Except in this case, we can tune the frequency just by changing the laser intensity. And so for a 10-meter cavity, for example, with this kind of system, you can potentially get to strains that are on the order of 10 minus 22 per root hertz, but only at frequencies above the band where LIGO is currently searching. And so this technique, we think, eventually will win out over the LIGO type interferometers, because the limitation comes not from laser shot noise, which is the case for the laser interferometers, but rather from the thermal noise in the motion of the trapped particle. So those different noise sources have a different frequency scaling. So while the LIGO detectors tend to get decreased sensitivity at high frequency, these sensors tend to actually improve. And so there'll be kind of a natural crossover point. So the idea is that there'll be potentially a way to extend the search for gravitational waves above the range where LIGO looks using this new approach. So we're building a 1-meter tabletop prototype detector to really put some of these ideas to the test. And so you might ask, well, what are the signals up there? So there aren't so many conventional astrophysical signals, but there are some possible candidates from physics beyond the standard model. And so one of those could potentially be due to, for example, annihilations of axions. So the axion is a hypothetical particle that would solve the strong CP problem in high energy physics, and also is a good dark matter candidate. If the axion exists, it can form clouds around spinning black holes through something known as the Penrose superradiance mechanism. And so for certain masses of axion, with a Compton wavelength sort of matching the size of the black hole, you can macroscopically populate a cloud of axions. The axion is its own antiparticle, and so it can annihilate into a graviton. And so this could give you a monochromatic long-lived source of gravitational waves that are right at, say, the 100 kilohertz sort of frequency range, which is matching roughly with our peak sensitivity. So in order to do this, it turns out that we want to be a little careful about engineering the size and the shape of the particles that we're using. So while most of the early work I talked about using spherical particles, it turns out we actually want to use a disk or a plate-like geometry to really maximize the sensitivity for gravitational wave detectors. We want a combination of a large mass, a large frequency, but also we want to minimize the heating from this light scattering or photon recoil. And so if you have a plate-like particle, you get primarily a forward and backward scattering instead of isotropic scattering that you get for a small spherical particle. And so this way, the light scattering tends to propagate back along the axis of the cavity, so you get less random heating effects from these type of geometry. And so this is a handle to potentially improve the sensitivity significantly. And so we've now shown that you can entrap very large aspect ratio plate-like particles. This is a picture of a sodium yttrium fluoride prism crystal. It's about 100 to 1 aspect ratio, 20 microns across and only 200 nanometers thick. And so essentially what it does is it stands up in the face of the, where its face is along the laser axis of the cavity. And so then you can study the motion of the particle in the different axes as well as the tilting and tipping motion. So you can define like a figure of merit. I'm going to go relatively quickly because I'm a little running out of time. But essentially, you want this combination of large mass, high frequency, and low light scattering from recoil. And so depending on whether you're dominated by thermal noise or the recoil noise, we've already shown that this geometry is already favorable in terms of this figure of merit for gravitational wave detection. And in terms of source modeling, for example, if you look at the Milky Way, for the rough estimate we have the number of black holes in the Milky Way, depending on their distribution of spins, it may be possible that we'll already be sensitive, even in our 1 meter prototype instrument, to potentially see some signals from axions, if they're there at the right mass. Okay, so going forward, this work is all sort of being done where the sensor itself is really still in the classical regime. It's possible to think about what you can do in the quantum regime. In particular, if we could potentially do matter wave interference with these types of nanoparticles. And so the current world record for the largest object that we've had behave like a wave instead of a particle are these macromolecules that are studied in the group of Marcus Arndt in Vienna, where we have about 25,000 atomic mass units. And so in principle, you could take a nanoparticle, and if you sufficiently cool it, you could drop it from its optical trap, diffract it from a grating, and then measure where it goes. And if you do this over and over again, in principle, you could generate an interference pattern, one particle at a time. And so if you do this, for example, near a surface, you can also use that sensitivity to potentially study these non-Newtonian short distance forces. So we're currently building a cryogenic experiment to investigate that. In the long run, this type of technique where you basically create a macroscopic spatial superposition of nanoparticles could potentially be used to look at other aspects of gravity, in particular to see whether gravity can act as an entity which entangles quantum systems. And so I think we're going to have a session on this later in the conference where we're going to hear more about these ideas. There's a lot of technical challenges that have to be overcome, but we're starting to analyze some potential configurations and parameters for this type of a setup. So let's see, how am I doing on time here? 1 minute. Okay, so yeah, I'm not going to be able to say too much about the other topic I wanted to say something about. So another technique that we're working on in the vein of precision sensing for beyond the standard model is to look for spin-dependent new fifth forces. So whereas the first example was more mass-dependent, and so in particular, axions are a well-motivated particle beyond the standard model, and the axion could be potentially dark matter. There are a number of experiments, the cavity type experiments, NMR type experiments, for example, that are running or being developed to look for axions as dark matter candidates. But axions also can create new spin-dependent fifth forces at short distance. So here's just kind of briefly some of the zoology of some of the current running and proposed experiments for searching for axions. This was part of the outcome of a study in the high energy physics community known as the SNOMAS process, where they developed a set of a roadmap, if you want, for searching for the axion over a wide variety of its potential parameter space. So in our lab, we're looking for a fifth force from axions that's due to basically axion exchange, where the axion is a force mediator between nucleons. In particular, you can create an interaction where the spin of one nucleus couples to the mass of another, essentially. And so in this way, because it couples to the spin, it kind of looks like a fictitious magnetic field. And so this magnetic field doesn't obey Maxwell's equations. In particular, it's not affected by magnetic screening, and so you can do precision magnetometry to search for it. Okay, so We're currently, I'm just going to go kind of quickly here. This is a basic idea for the experiment. So you have spin polarized helium-3 nuclear spins in a gas, and we have a source mass here. So it's just an unpolarized tungsten cylinder. So just to show you the basic idea, basically you have this spinning tungsten wheel with these teeth in it, and as the teeth pass by, they excite spin precession in the helium, in particular when the frequency of the teeth matches the nuclear Larmor precession frequency of the sample. And so then you need magnetic shielding. In our case, we're using superconducting niobium to block regular magnetic fields, and then a squid magnetometer to read it out. The ultimate sensitivity, we think, will be limited by the quantum spin projection noise. And depending on what sort of T2s we can get for the system, we're anticipating being able to get down into the parameter regime here where one might expect to find the QCD axion for creating basically new forces in this kind of millimeter range. Okay, so maybe I'll go ahead and kind of jump to the end here, and if people want to ask more questions about this, I can come back to it. So to keep in the spirit of keeping on time, so we're testing various components for the system that are kind of the key parameters to show that we can meet some of the design sensitivity specs, and the cryostat construction we're hoping to complete in this coming spring, hopefully commissioning the experiment sometime to summer to fall of next year. Okay, so let me jump here to the end. So basically we're doing a number of AMO-based experiments to look for new beyond standard model physics, including tests of gravity, and also looking for new novel spin-dependent interactions, where when you combine our method with other existing efforts in the community, in principle, in the next coming decade or so, one could potentially cover the entire parameter space with the axion, which I think would be pretty interesting. So with that, let me just acknowledge our funding agencies and my group, and thanks for your attention.
Thanks, Andy. Questions?
Yeah, great talk, thanks. To what extent can going into the weightless environment of space advance the sensitivity that you could achieve with this instrumentation?
Yeah, so I think the obvious place to me where you'd make a fairly big impact would be this idea with the matter wave interference experiment. So there, at least in our initial test, we have a 20 centimeter drop path in our lab, and that's going to set some time limit on how long you can do the experiment. So at least among the ones that I mentioned here, that would probably be the most natural choice for, and I guess it's similar to kind of atom interferometry in space, the same sorts of advantages you have there.
Could you again explain the sources in the kilohertz and higher range? I didn't quite understood how. So you have this cloud.
For gravitational
you
waves?
have a rotation black hole cloud. I don't understand.
Yeah,
so
I went a little bit quick there. So there's a process called Penrose superradiance, where basically if you have a spinning black hole within the Milky Way.
But why is there a gravitational wave?
So you basically have this macroscopically occupied cloud around the black hole, and there's a process where you can have annihilation. So axion is its own antiparticle, so it can annihilate and form into a single graviton. So the frequency of the graviton is twice the mass, essentially, of the axion. And so that gives you a very monochromatic, long-lived signal at double the mass of the axion, essentially, which for a grand unified theory scale axion turns out to be right around 100 kilohertz.
What about other sources?
Yeah, so you could also have primordial black holes. For example, solar mass or subsolar mass black holes could give you signals there. If in the future we develop a bigger version of the instrument to, say, 10-meter scale, you might be able to measure frequencies down to a few kilohertz and maybe look at neutron star in spirals or things like that. But at least at the moment, 100 kilohertz is kind of for the 1-meter instrument where we're targeting.
So for that range, you would not have any astrophysical sources?
Yeah, I'd say there's not really any known conventional astro sources at that frequency.
Thank you.
But there could, primordial black holes may be part of dark matter, for example, so we don't really know.
Thank you for the great talk. Just have maybe silly question. You are looking for some difference between standard model, just standard gravitational force, and something just it's maybe different. So just, but you have, you can have just two choices. If just you have some different from the general relativity theory, or if you have some, for example, distribution of dark matter, that's maybe you don't know how it is distributed around this some object, but it can influence on the gravitational force. So just you have some difference in your data. That's at maybe two reasons. One of that that's some just that's general relativity not so just precise, and second reason that's this dark matter that's around this object that's maybe just it's close some deviation from the just classic force.
Yeah, no, it's a good point. And most of the gravitational deviation tests we're doing are these really short distance effects, right? So they're not. But if you have this fifth force field or whatever, that could be potentially a component of dark matter in principle, right? But yeah, in terms of GR, I mean, I'd look about it more as an equivalence principle test, essentially, whether you have this new kind of fifth force.
Thank you.
Yeah.
So if the laser cooling both lowers the Q of the levitated particle and decreases the temperature, is there a sort of a good amount of laser cooling that optimizes some other effects?
The good amount for us is the amount where you're no longer, where you don't want to be limited by detection noise, right? So the argument why we're able to beat advanced LIGO or whatever is because we're not photon shot noise limited. We don't have a problem resolving the motion of the particle because the high Q oscillator moves around by quite a bit on resonance. And so you basically want to do cooling to kind of broaden the line, which makes the experiment easier. But at some point, if you do too much cooling, you start to become potentially detection noise limited, and you lose the resonance effect that you're trying to do. Yeah.
Maybe following up on that a little bit. Sorry, lost my train of thought. Like, could you do cooling and then turn off the cooling and then have kind of your high Q and low temperature?
Well, so we've done experiments like the other groups have done that as well. Like in the data I showed earlier, where they measured the recoil from photon recoiling. So essentially, yeah, if you turn off the cooling, there's some finite amount of time it takes to heat up, and it'll be a combination of this fundamental recoil noise plus any kind of other technical noise, laser intensity noise, et cetera, et cetera. So yeah, we haven't really, at least for what we're doing so far, we've been pretty much looking at just sort of steady state force measurement, but in principle, you could do some trick, I suppose, for kind of short measurement time type. I guess it depends on what signal you're trying to look for.
And then my original question actually was, to what extent does the internal temperature of the particles matter for these experiments?
Yeah, it's a great question. So once you're in kind of the high vacuum regime, there's a pretty good decoupling because there aren't too many gas collisions to transmit the information about the center of mass temperature to the internal temperature. In practice, there's limitation because the particles will heat up in vacuum just due to finite absorption of the laser. And so then there's a balance that you eventually hit between black body emission from the surface, counteracting with the absorbed light from the laser. And so that sort of sets a limit in terms of how high intensity you can operate. In other words, how high frequency you can operate. So for the gravitational wave detector application, that's actually a constraint which stops us from going up to kind of, say, the megahertz regime higher than where we're going to operate. So we're actually working on, I didn't mention it, but ideas to use levitated materials that have internal solid state cooling or anti-Stokes fluorescence cooling. Also sometimes called laser refrigeration, where you can in principle have the trap itself cool the internal particle. Then maybe you could do higher intensity, but that's essentially what it's sort of a limit on how hard you can trap it.
Thanks.
What sets the limit on the axion mass that you're detecting?
Well, so in the gravitational wave experiment, it's it's basically the mass of the axions determining the frequency of gravitational waves. So it's more like our frequency sensitivity band is determining which masses of axion. In the other axion experiment, there it's the Compton wavelength. So the mass is related to the Compton. So the interaction range between our helium-3 sensor and the nearby source mass needs to be within the Compton wavelength to be sensitive to an axion with that particular mass. So it's not like, say, the cavity experiments where you have to tune the cavity to resonantly match the dark matter oscillation frequency. We can search a bunch of frequencies at the same time as long as they're within the range.
Thank you.
Very interesting. So I've also heard about these magnetic levitation techniques to sort of hold these things in place. Can you comment on the relative pros and cons of those?
Yeah, I mean, so it's another possible approach. There are other groups looking at doing magnetic types of levitation. So I think it depends on, you know, what your target goals are. At least for these gravitational short distance tests, we found that we want to sort of eliminate magnetic backgrounds, and so we prefer to have a non-magnetic system. But yeah, in principle, you could get magnetically levitated particles into the quantum regime and do interesting things with them as well.
Thanks.
Right. There's a lot of things to go about.
And I always had this question, which I'm confused. You know, what are you going to use to read out these nanoparticles? You know, in the end, you're still going to do projective measurement by using photons, right?
Yes. Yes.
And those photons, I used to know, you know, interferometry is the best way to measure distance change. And so when you have a nanoparticle, gravitational wave comes, you have a little oscillator which can be amplified a little bit. But in the end, you still have to measure where it is.
Yes, yes.
And that measurement itself will have a lot of noise. The photon shock noise will still come in. And so maybe you can tell us a little bit about it.
Yeah, absolutely. So there's different approaches to measure the position of the particles, and we use different approaches in different experiments. But for the gravitational wave experiment, we basically use the Pound-Draver-Hall reflection signal. So the idea is that you have, as the particle moves in the around in the cavity, you get a phase shift of the light reflected from the cavity. So if you monitor we actually have two lasers, one to trap the particle and a second one that we use to read it out and cool it. And so that readout beam essentially is sensitive to through the phase, basically through a dispersive effect. And so yes, we are definitely limited by shot noise on our measurement there, but because the particle moves so much, we're not close to the shot noise limit.
Okay, so yeah, in the spirit of keeping on time, let's call it that. Thanks, Andy.